Let's investigate what happens when we graph the inverse of a function on the same axis as graphing the original. So if we started off with the equation y equals 3x plus 6, so that is a line with a y-intercept of 6, so 1, 2, 3, 4, 5, 6, and we have a slope of 3, so we end up with a graph that looks like this line. Now, we want to graph the inverse on the same axis, so we need to have an inverse equation. So when we find an inverse equation, we're going to switch x and y and solve. So there I switched x and y. Let's solve for y now. So we subtract 6 from both sides, and now we're going to divide by 3. Now, the way that this is written, this equation that we have, x minus 6 over 3, is not helpful for us to graph. So I'm going to want to split this up. So 1/3 x minus 6/3, but 6/3 is 2. The reason I wanted to split that up was so that I could get the y-intercept and the slope so that I can graph this easily. So the y-intercept is -2, and the slope is 1/3. So I'm going to go up 1 and over 3. Now, if you graph accurately, every single time that you graph a function with its inverse on the same axis, you will actually catch a line of symmetry. It's sometimes hard to see. Some types of equations make it easier to pick out. Others make it a little bit more difficult. This one isn't too bad to see. It's actually symmetric across this diagonal line in the middle. If I had this set of axes on a piece of paper and I folded this paper in half, I would end up having a mirror image over this line. And this line is the line y equals x. There should be no surprise as to why we are symmetric over this line y equals x, because in our equation to find the inverse, we took x, we took y, and we switched them. So in the inverse equation, x is y and y is x. So they are reflective across the line y equals x. Now there's a couple other characteristics that you can get from graphing an inverse on the original graph. You'll notice what happens with some of the points as well. So let's just pick a point. More specifically, let's actually pick the y-intercept on the original. That was the point 0, 6. Since we take x and y and switch positions, if I were to switch those positions, I would have the point 6, 0. And that is a point on our inverse. So this is g of x. I should have labeled them. And this is going to be the original. The point that I'm trying to make is that when we have an original graph and we know coordinate points from that original equation, those points will almost be seen on the inverse graph, but in reverse order. The sign of them does not change. They literally just switch positions. And so what that means is if we have a y-intercept on the original graph, that's going to become an x-intercept on the inverse graph. The domain of the original will become the range of the inverse, and vice versa. And that is all because we switch and we flip over the line y equals x. So x becomes y and y becomes x.